Hi guys, it's Professor Stevens. I'm going to be going over how to understand function symmetry and even and odd functions. And I'm going to start by referring to notes from our last class that need to be corrected over here on the side of origin symmetry. So we were looking at this function y equals x squared plus 3, and we were using algebraic methods to figure out if it was symmetric, and if so, in with respect to which axes or to the origin. So the tests for testing symmetry are similar to the tests for testing whether a function is even or odd. So I'm going to go over those tests so that we can clarify. So first of all, if you want to know if a graph is symmetric with respect to the y-axis, then replacement of x with a negative results in an equivalent equation. If you have something that's symmetric with respect to the y-axis, it just so happens that also makes it an even function. And even functions have the quality that if you replace it, this, as it's stated right here, f of negative x is equal to f of x. So that's exactly what was stated up here, just stated in a different way. Replacement of x with negative x results in an equivalent equation. And that's what we see right here. Plugging in a negative x results in a regular, in what you would normally get plugging in a positive x. Then we have testing for origin symmetry, and it says if the replacement of both x and y with negatives, you get the same equivalent equation result, then we say it is symmetric with respect to the origin. Likewise, if you have a function that has origin symmetry, that also makes it odd, an odd function. And the way that the definition of an odd function is written here is that f of negative x will result in the opposite version of the original function. And that is the same thing as what we see up here, because notice that when you replace negative x in the input, you get back negative y, because remember f of x represents y. So this is just saying if you replace negative x, then you get back negative y, or anytime that the sign of your x is changed, you have to also change the sign of your y to get a point that is still on the function. And what does that really mean when you graph these? So let's look at the graph of an odd function. So let's look at f of x equals x cubed. This has origin symmetry. Notice that if I put on the point -1, or actually let's start with +1, 1, comma 1, right there. And I also put in -1, comma -1. Notice that those 2 points are each on the function, and that it is across the origin that you have a mirror image. Another way of seeing this is that if you rotated this picture upside down 180 degrees, it would look exactly the same. So that's what origin symmetry means. Changing the sign of both x and y results in a point across the origin still on the function. Now let's look at an even function. So let's look at f of x equals x squared. This has symmetry to the y-axis, and it is an even function. And what happens if I put on 1, comma 1, and then -1, comma 1. Now notice this time on the second point, I only changed the sign of the x value, and the y value is the same. So we have symmetry across the y-axis. I could use other points too, like 2, comma 4, and -2, comma 4. Right, and so you'll see that that will always happen with an even function. Right, so those are two types of symmetry that also correspond with another concept. So some symmetry with respect to the y-axis makes it even, and symmetry to the origin makes it odd. And then there is another type of symmetry which I didn't actually review here, and that is symmetry to the x-axis. And symmetry to the x-axis, actually, let me think of one for us for that. Let me just pause this for a minute while I get a good example up. Okay, so the example I pulled up here, or I'm about to pull up, will show us symmetry with respect to the x-axis. Now notice that in each of these it says for symmetry the equation is symmetric with respect to the y-axis if the replacement of x with negative x it says the graph of an equation is symmetric. And then down here when we talk about even functions, the word function is used rather than equation. Also want to show that here, same thing with being symmetric to the origin. The word equation is being used here, and then in the context of being odd, we're talking about an odd function. The word function is used here. Then we have an equation which would be symmetric to the x-axis, and the test is that if you replace y with negative y, it results in an equivalent equation. So what this means is that the sign of the y gets changed, but the sign of the x will stay the same. And when we have x-axis symmetry, it actually is not a function. An equation that has x-axis symmetry is not a function, and we don't discuss any quality of it being even or odd or anything like. There's no type of definition that goes along with x-axis symmetry regarding functions, because it actually will never be a function if there is x-axis symmetry, because anything that is symmetric to the x-axis, such as x equals y squared, like this, x equals y squared will have x-axis symmetry, right? If I have, say, 1, 1 and 1, negative 1, this is going to fail the vertical line test, although you do see that we have x-axis symmetry. So an equation can have x-axis symmetry, but that equation will not be a function. So that's part of the reason that might help you remember why only when we're discussing y-axis symmetry do we have a corresponding definition regarding an even function, and origin symmetry having a corresponding definition regarding odd functions. So that is an overview of symmetry of equations and how that relates to certain types of functions that have special names. So we've been able to identify even functions, ones that are symmetric to the y-axis, and odd functions that are symmetric to the origin. They have special terminology assigned to those. All right, so back to the example I was working on in class. We were doing the x-axis symmetry where we replaced the sign of y with negative and found that it did not result in the same original function, so we said no, it does not have x-axis symmetry. Then we looked at the equation to see if it had y-axis symmetry, and we looked to see if we replaced negative x in the equation, if it would result in the same, and yes, it did result in the same, so we said yes, it has y-axis symmetry. Then going on to origin symmetry, this is actually more appropriate when you're talking about odd functions, and this part of it, I kind of mixed up the two definitions here, and I said all signs change. Well, actually, all signs change applies to this part of it up here when you're dealing with odd functions. But when you're just doing it from the perspective of an equation with origin symmetry, you would actually change x and y signs, both of them, and see if you get the same results. So I'm just going to fix that. And what happened when we plugged it in? Notice that we did not have a resulting equivalent equation. That is not the same as the original that was given. The original that was given up here is y equals x squared plus 3. So that would mean that we do not have origin symmetry. No origin symmetry. And it also means that it's not odd, but the test we would do for determining whether it's odd looks slightly different, even though it means the same thing. So I'll do that down here. Or actually, I'll do it on the next page. So is y equals, what was it, x squared plus something? Let me just double check. X squared plus 3. Is x squared plus 3 an odd function? So if it was worded this way, we would say, well, let's see, f of x is function notation, so we're just replacing y with f of x, and then we will want to see if replacing x with negative x results in negative y. So we'll go through the process here. F of negative x is equal to negative x squared plus 3. Which, when expanded, we can see that this becomes a positive x squared, and this is not equal to negative f of x. So therefore we say no, this function is not odd. Okay, and just to drive the point home a little bit harder to make sure it's clear, the other type of question is to say, is y equal x squared plus 3 symmetric with respect to the origin? So the test we will do is we will replace x with negative x and replace y with negative y and see if simplifying results in an equivalent equation. So that's what we'll do. So we are not using f here because we're not thinking in terms of functions, we're thinking in terms of equations. And we'll start by taking our y and putting negative y instead, taking our x and putting negative x instead, and then we'll simplify. So again, we'll see that this side turns out to be positive x squared plus 3, and then to solve for y, we would divide by negative 1 throughout, so then we would have y equals negative x squared minus 3, which is not the same as y equals positive x squared plus 3. Right, so not the same, therefore this equation does not have or is not, let's say it like this, is not symmetric with respect to the origin. And let's look at the graph of this function as well. For f of x equals x squared plus 3. Okay, so you can see here that it does have y-axis symmetry. It does not have origin symmetry. If you flip this upside down, it would not look the same. If you just spun this entire paper around the origin, upside down 180 degrees, you would not have the same function. So it is even, it is not odd, and that concludes this part of the lesson. Thanks for watching.